Hello everyone, my name is Debbie Cepeda and today we will be going over a lesson that is Introduction to Electric Machines for Automotive Applications. We will start off by asking, what is an electric machine? An electric machine can either be used as an electric motor or an electric generator. So now you ask, well, what is the difference? An electric motor converts electrical energy into mechanical energy, where torque results from the interaction of a magnetic field with an armature current. For example, a fan that you use to cool yourself during a hot summer day. You plug it up and the fan rotates. You unplug it and it stops working. Without providing voltage to the fan, current will not be produced to convert electricity to mechanical torque. An electric generator converts mechanical energy into electrical energy. So according to Faraday's law, voltage is induced in an armature coil by a time-varying flux as seen by the coil. Let us now look at some examples of how an electric machine can be used in vehicles. Many functions on the vehicle that were previously operated manually or perhaps mechanically now use an electric motor. For example, most vehicles have power windows that previously required the individual to roll down the window. This is especially useful if the driver wishes to lower the windows in the back seat while driving. There are many other applications that are under the hood of your car. For example, many modern cars use electric water pumps rather than mechanical pumps, formerly driven by a belt connected to the engine. The use of an electric motor is a more efficient solution, especially as the speed of the pump impeller can be changed as the coolant temperature varies. In a vehicle, an electric motor can be used to start the engine, which will be our main focus for this module. An electric motor also provides tractive power for propelling electrified vehicles. Other applications of an electric motor are power seats, heater fans, and windshield wipers. So as you can see, they come in all sorts of sizes. Let us remember that the electric machine can also be used to generate electricity that charges the 12-volt battery for sustainable power. One such example is the alternator. On a larger scale, an electric generator charges a high-voltage battery pack on an electrified vehicle by regeneration, where kinetic energy is recovered rather than dissipated as heat in the brakes. Another useful application of an electric generator powered by the engine is onboard power, where the system can provide electric power, possibly in remote locations, to other electrical loads. Now that we have briefly discussed several applications for electric machines in today's cars, let us address the advantages of using electric motors for propelling our car, whether it is an all-electric vehicle or a hybrid. As we will later see, the electric motor can be extremely efficient, even greater than 90%. We may compare this with our internal combustion engine that has an efficiency of about 30%. Another advantage is that these vehicles produce less pollution than a gasoline-powered car that poisons our environment. Electric motors are considerably quieter than the engine and are considerably more reliable and require less maintenance. The electric motor is also much lighter weight than the engine for comparable energies. As more charging stations become available, the convenience of being able to charge your car while grocery shopping is a great incentive, especially if the electricity comes from a complementary charging station. The two illustrations in this slide provide a comparison of the performance of the engine and the electric motor. We first note that the engine must operate at an idle speed of approximately 800 RPM before power can be provided. This is in contrast to the electric motor that can provide maximum torque at locked rotor, that is, when the rotor is prohibited from turning. This characteristic is ideal when first starting from a stop sign. It is possible to operate the electric motor at maximum torque up to a speed that is referred to as a base speed. It is at this speed that the motor reaches its maximum allowed power. Let us recall that power is the product of torque and speed. So past this base speed, we can continue to operate the motor at consistent power. However, it is necessary that the torque decreases inversely proportional to the speed. Thus, the motor's performance can be divided into a constant torque region and a constant power region. In contrast, we see that the engine produces its maximum power close to its maximum allowed speed. In this figure, the torque speed curve for a somewhat different type of electric motor is presented. In the previous slide, a somewhat ideal performance for an electric motor was shown. However, it is fairly representative of a permanent magnet brushless DC motor that is frequently used in automotive applications. The characteristics shown in this slide are for an induction machine that is also used for electrified vehicles. You may note that the torque initially increases somewhat with speed from the stalled position. The torque speed curve for a nonlinear load has been inserted to demonstrate how an operating point occurs at the intersection of these two curves. Another representation of the torque speed characteristics for an electric motor is shown in this figure. The various colored regions in the illustration correspond to efficiency bands. One may note that the maximum efficiency occurs in the dark red region, which is oftentimes called the sweet spot, and here has an efficiency of 93 to 95%. Obviously, it would be highly desired if the motor could be operated a significant amount of time in this region. With some hybrid configurations where the motor can be operated in the generator mode at one specific speed, this optimal condition becomes possible. It should be noted from the figure that the efficiency is considerably less when operated at small loads or at very low speeds. This behavior is somewhat similar for the engine. The demands on an electric motor used in a vehicle are typically much different than a motor used in industrial applications. For example, industrial motors are frequently operated at a rather constant speed and load, and frequent rapid starts are seldom required. In contrast, the electric motor used in electrified vehicles experience frequent starts and stops with steady driving, rapid acceleration and deceleration, high torque requirements when climbing a steep hill, and low torque, high-speed cruising. These different requirements require that other design criteria be employed. Another major concern is that weight is a major concern for vehicles as it affects fuel economy and performance, while the motor's mass is typically not important for stationary applications. Since the development of the electric motor in the 1800s, as well as electric vehicles, which were quite popular around the turn of the century, considerable technological improvements have occurred. The popularity of the electrically propelled vehicle declined toward the first of the 1900s because of improvements made with internal combustion engines and limitations imposed by the electric motors. So to be able to control the speed of the electric motor, brushed DC motors were the only candidate. Unfortunately, these motors were relatively inefficient, especially because of the rheostat used to control the speed as well as losses at the brushes. The motors were also considerably less reliable than what we have today. These concerns were overcome with several enabling technologies that principally include the discovery of better magnetic materials, power electronic devices, and digital controllers for managing the motor. With their advent, variable speed AC motors became possible and the brushes could be eliminated from the motor. In this slide, motors are classified as either being DC or AC. The DC motors employ a commutator which requires brushes to make the electrical contacts. These motors are sometimes used for applications such as golf carts and similar types of vehicles, but find limited use for regular vehicles. The AC motors, on the other hand, have several candidates that have proven to be quite useful and use three-phase inverters to convert the DC power to AC. The induction motor is a particularly rugged machine and has proven to be quite useful for automotive applications. AC synchronous motors, as contrasted to asynchronous induction motors, have also gained considerable prominence. Of particular interest is the permanent magnet brushless motor. Shown here is an alternate method of classifying electric machines that is as to whether or not they have a commutator. The commutator is much less desired as we have previously discussed. Perhaps I should note that the term synchronous implies that the motor speed is exactly related to the applied AC frequency, while such is not the case for the asynchronous motor that rotates at a slightly slower speed. As we have just mentioned, motor types have been selected for discussion that have application in electrified vehicles. In particular, we will examine the permanent magnet brushed DC motor, the permanent magnet brushless DC motor, the induction motor, and the switch reluctance motor. As you may now suspect, they come in all shapes and sizes. So, starting with the major advantages, disadvantages of the various types of tractive electric motors, DC machines are no longer used in production vehicles because they have low efficiency and maintainability, and they are only used by hobbyists and for unique applications. AC induction machines are frequently used and they are very rugged. The induction machines are less expensive, but the electronics are expensive. For the permanent magnet brushless DC machines, also known as PMDC, are very efficient and compact, also frequently used. Both machine and electronics are expensive. Switched reluctance machines are not used in today's production vehicles. However, there is ongoing research that shows potential they will be in future cars. The machines are less expensive because of a simple rotor design, but the electronics are expensive. Looking inside the brushed DC motor, we see a commutator on the rotor with divided conductive segments that selectively energize specific rotor windings. Contact with these segments is made by carbon brushes that provide electrical continuity while at the same time permitting rotation. A constant magnetic field is supplied by the stator. It can either result from a permanent magnet or a field coil mounted on the stator that receives DC power to create the magnetic field. A permanent magnet is chosen in this slide for comparison with the configuration shown in the next slide. Looking inside a permanent magnet brushless DC motor, the magnets are located on the rotor so that an electrical connection is not required to this rotating component. The magnets may either be mounted on the surface or the interior of the rotor. Rare earth magnets are typically used because of their high field strength. The armature coils are mounted on the stator. This configuration has an added advantage that cooling requirements are simplified since there are no currents on the rotor. The speed range is similar to the brushed DC motor. The motor is relatively expensive because of the cost of the magnets and the electronic motor drive. Shown in this slide is a comparison of the brushed and brushless DC machines. Let's remember that the permanent magnet brushless DC motor is really an AC machine, but gets its name because of several similarities with the brushed machine in terms of principle of operation. While the brushed machine has a physical commutator that serves as a rotating switch employing carbon brushes, we can envision that the brushless machine likewise has a commutator, except that it is electronic and operates by sensors that detect the relative rotor position, and electronic circuits produce the required electrical waveforms. Looking into the induction motor, we see that it has a stator and a rotor. The rotor may be either wound with wire or comprised of a number of thin bars mounted on a laminated cylinder. This latter configuration is called a squirrel cage rotor. The bars are connected together with a shorting ring at each end of the rotor. The rotor and stator are separated by an air gap, which allows free rotation of the rotor. The rotating magnetic field is generated by an AC voltage to the stator winding. This magnetic field induces a voltage in the rotor bars, which in turn produces a current. The interaction of the current with the stator field produces a torque to turn the rotor. The induction motor is well suited in applications that require wide speed ranges. They are relatively inexpensive and provide good control, although the electronic motor drive does significantly increase the cost of the system. A switch reluctance motor contains neither windings nor magnets and can deliver high power density at a relatively low cost. Torque is provided by poles on the rotor that attempt to align with the poles on the stator so as to minimize the reluctance of magnetic circuit. As the stator field rotates, the rotor chases the field in a continuing effort to align. The reluctance in the magnetic field is analogous to the resistance of an electric circuit. In order to maintain the rotation, an electronic control system switches voltage on the winding of successive stator poles in the sequence such that the magnetic field of the stator leads the rotor pole, pulling it forward. The motor has the disadvantage of significant torque ripple that appears as cogging, resulting from the difference between maximum and minimum torque with the rotor rotation. This also produces acoustic noise that further contributes to its limited use. However, promising research is being conducted to minimize this deficiency.